Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Dr. Pascal Paschos, who is a computational scientist at the University of Chicago and an instructor of mathematics and computer science at Chicago State University. After 12 years in academic research at UC California, San Diego on computational cosmology, he moved to Chicago, where he worked in high-performance computing at Northwestern University. Later, he joined the MANIAC lab at the University of Chicago, where he is involved in accelerating computational research using advanced cyber infrastructure for several international high-energy physics experiments, and serves as the Open Science Grid Area Coordinator for Midscale collaborations. Welcome, Pascal.
Hi, Gill. Nice to be here.
I want to start with a couple of papers that you're involved in. The first one, distributed computing software and data access patterns in OSG, mid-scale collaborations. OSG is Open Science Grid. What exactly is Open Science Grid?
Open Science Grid is a federation of university and academic institutions around the country that are coordinating in allowing other institutions, including their own, in accessing computer time on their local computer infrastructure. So every institution that has a deployment of some kind of a computing system, and we're talking about clusters or high-performance computing, supercomputers and stuff like that, they are making that infrastructure available to everybody who has access to this Open Science Grid. And you don't have to be a member of the participating institutions, but every academic researcher out there in the United States can gain access to the Open Science Grid through, there are some, what we call submission hosts, machines that are dedicated to providing access to researchers. The only condition is that they have to have a project, a computationally based project for their academic research. And it is an extension or something equivalent to another distributed computing infrastructure called XID, which is instead of being across all academic institutions, typically tries to create an infrastructure of very high-powered data centers and computer centers around the country. There, getting access is a little bit more complicated because you have to make the case that the existing the infrastructure that is provided, you can make some use of it. Like you have codes that can scale up to thousands of cores of computational on computational systems, and you can get some cutting-edge science done on it.
So this is almost like sharing idle compute capacity.
That is correct.
So I remember, I don't know if this still exists, long time ago, the search for extraterrestrial intelligence used to have some sort of a program where you could actually put your home computer available for for analysis, right?
I actually ran this on my computer back in the 90s,
Yeah.
late 90s for that. Yes, I remember that.
Yeah. So
it is similar from the point of view that the individual institutions allow code to run on their systems, but the origin, who is doing that, is multidisciplinary across multiple institutions, and so there's not a single program that runs there, right? So, but the process is similar from the point of view that I have an infrastructure, computing infrastructure. I have computer cycles available to spend, and it makes sense from the IT leadership perspective that you don't want your machinery to be sitting idle.
Yeah.
I mean, these are multi-million investments, so you are enticed to contribute this to the broader academic community, not just because you're advancing science, but there is also mandates or strong encouragement by the federal government through their National Science Foundation, where they are encouraging universities, when they deploy, for example, a cluster, to make a portion of that time available to the broader academic community.
Okay, so all U.S. universities are part of this, or just a subset?
No, not all U.S. universities have that, but every U.S. university that has a cluster has or some kind of a computing infrastructure has the opportunity to join the Open Science Grid.
Okay.
And not only to facilitate their own researchers to get access to that, but also, you're becoming a digital citizen that contributes to the broader effort for pushing the limits of science.
Right. And what do you mean by a mid-scale collaboration?
Right. The scientific collaborations out there have different scale in terms of how many institutions are partners in that collaboration.
Yeah.
And what is the scale in terms of computing needs that they have for their computational workflows to run on. And so, to give you an example, the Atlas collaboration or the CMS collaborations, which are experiments running in CERN, looking in high energy physics, are considered to be the extreme end of a large collaboration, because it involves hundreds of institutions and hundreds or thousands of researchers working on that. A collaboration, for example, like Xenon, is an experiment that is running out of a national laboratory in Italy. It is an international collaboration. It has partnerships with academic institutions, including University of Chicago.
Yeah.
But the scale of how many people are involved there, it's much smaller. But it's not small enough from the point of view that you have an isolated collaboration of a couple of universities. There is not really a clear-cut number of how you can separate like a mid-scale, small-scale, and large-scale collaboration.
Yeah.
But the area of responsibility in my case is that those collaborations that are not the extremely large ones like Atlas or CMS, but they're not the very small ones, which are partnerships between 1 to 2 institutions.
Okay, so it's both the number of institutions involved, number of people involved, as well as probably the amount of data involved.
Amount of data and amount of computing time that they will need to spend on a yearly basis.
And the amount of computing time. Okay. And so this is sort of an exclusive type of a network that is kind of dedicated to just this, or is it piggybacking on something that already exists?
You mean like a network, network used for transferring data?
Yeah.
Okay. It's piggybacking on existing infrastructure.
Yeah.
However, the Open Science Grid has a partnership with Internet 2, and Internet 2 is it's a network company, but it's not for profit. Its address is internet2.edu. So it's an academic. Their customers, the clients, is basically the academic institutions. And what Internet 2 does is provides access to institutions to a high-speed internet pathways across the country, and is responsible for managing those pathways and the endpoints. And there is this partnership between Internet 2 and Open Science Grid to facilitate and augment existing transfer capabilities and network capabilities that these universities will have to rely on to move the data around. Because the number one, I would say, I wouldn't call it problem, but challenge in working in this federated cyber infrastructure is how do you move large volumes of data from one institution to another to be able to process them on another cluster and then get the results back.
Right, right. And so Internet 2 is part of the infrastructure. Do you actually move data on the regular internet?
Yes, there will be a portions of the data. It depends on the size of the data, right?
Yeah.
There will be small size files that do not need to use any high-speed connectivity. I mean, the pathways between across the countries will always run what we call 100 gigabit lanes or even more.
Right.
But smaller files, they don't need to access those very fast lanes, and they can move over a slower network. We don't actually, even though we have monitoring in place to capture all this information, we don't immediately have a feel of how one institution talks to another institution.
Right.
And so the typical way that this is happening is that in the Open Science Grid Federations, you will have what we call submission hosts, locations across the country where researchers from different universities can log in and use that as a gateway to the broader cyber infrastructure. And so what it really matters is that submission host moving data, is it on a high-speed network? How does the data flow from there to the rest of the infrastructure?
Okay. You have another paper with your colleagues. It's entitled Creating a Content Delivery Network for General Science on the Internet Backbone Using X Caches. So you say that there's a general problem faced by computing on the grid for opportunistic users is that delivering cycles is simpler. Computing cycles is simpler than delivering data to those computing cycles. So this is sort of a new technology.
The caching technology, conceptually speaking, is not old at all.
Yeah.
I mean, your internet browser on your machine is caching all the time.
Yeah.
And to make delivery of data to your local machine as fast as possible, because if you keep on using the same, for example, website, loading a bunch of stuff there, you do not want every time you load this page to go and bring the same images or the same content again and again and again. So if you can cache a lot of this information that is frequently used on your machine, then loading up on the information on your browser becomes much faster. So the idea of caching for cyber infrastructures like that is that a lot of the times collaborations that basically generate experimental data, they are multiple users will need to access the same kind of data. They're going to do different science with the data, but the data stays the same.
Yeah.
Right. And so the whole idea is instead of every time a user or a researcher needs to grab a portion of the data and send them someplace else to analyze them, we can cache all this information in a piece of infrastructure called the caching layer. And then which is distributed around the country. So if a job runs on an institution, instead of going all the way to where the data originally was created and stored, it can go to the nearest caching location and basically bring the data from there. So that basically makes the data much more readily available on the institution where the jobs is running, the computational workflow is running. And so you don't spend much of your time moving data around. You basically spend most of your time actually doing what you're supposed to be doing, which is actually computing.
Right. And it's not human directed, right? So will the machine know where the nearest and most optimum cache might be for a specific data?
Yes. There is always a human intervention in terms of like diagnosing problems like that. But of course, this whole thing is automated from the point of view that is algorithms that is written in the infrastructure setup that will recognize where your job is running and also find out the nearest caching location from where that is in proximity to the institution where you're running. And of course, there will be cases where the data that you request may not be in that caching location readily available. In that case, data can be actually found from another caching location or going all the way back to what we call the origin, the place where the data originally are stored by the collaboration. But bear in mind, once you actually do the calculation once and you bring the data into that nearest caching layer, caching location, then next job that you're running, you don't have to go all the way back up and get them. You can get the data from, since you have populated the cache with the data that you needed for the calculations.
Yeah, and the beauty here is from an efficiency perspective, every time you run an experiment, let's say combining multiple data sets, you are creating possibly a new data set that could be cached, that could be I'm just speculating, Pascal here, that could be built on by somebody else at a future time.
That's right. I mean, the experimental data go through multiple stages of analysis and processing.
Yeah.
Raw data need to be processed, noise need to be removed, they have to be cleaned up. So, and this data, before they even become like production quality data, they have to go through through a couple of layers of, what we call a reduction process. And if we can have a pipeline where this thing is automated, where this whole thing gets cleaned up and then becomes available to the researchers, we do not need to keep the old data around, and and that greatly increases the efficiency, because if I were to do a computational workflow, but I don't need the actual raw data from the beginning, I need like data generated 2 or 3 levels down in terms of processing, I can go and grab the process data rather than the original one, and that of course expedites the whole the path towards the final result.
Okay, and even the computational cycles, where the computational cycles are available, are also algorithmically driven. So if you submit a job, it can then find where the cycles are. It can find where the optimum cache might be.
Yes.
Yeah. Okay.
Although the users do have some control designating where they would like their jobs to run, this is handled by some centralized services within Open Science Grid called the factory operations.
Yeah.
And the factory, what it does, it basically accumulates jobs from users submitted, and it determines where the available cycles are and sends the jobs there.
Okay.
So in fact, when jobs are running by users in endpoints within the Open Science Grid, they're anonymous. There's not really any user information. It's packaged by the factory, sent there, and then the user just basically gets the results back to the location where they submitted the jobs from.
Right. Yeah. And again, when a new data set is available, multiple people may want to work with that data, maybe run different experiments, look for replication. This type of infrastructure allows all of that to be done pretty quickly.
I wouldn't say necessarily pretty quickly, but definitely more efficiently.
More efficiently. Yeah. Okay. I want to get into a few of the projects you've been involved in. One is in the South Pole Telescope, and that is the Cosmic Microwave Background (CMB), analyzing the CFB data, looking for temperature and polarization. Could you talk a bit about that?
Well, yes, the South Pole telescope is going through several iterations. It's an instrument down in the South Pole, as the name indicates, actually dead center in the South Pole, and there is always staff there, taking measurements of the cosmic microwave background. And the first survey, as far as I remember, was done back in the 2011, and since then they have been continuously upgraded. They're upgrading the cameras there, and therefore, the efficiency and the sensitivity of the instrumentation.
Yeah.
And as you improve sensitivity, the challenge there is that you're collecting more data, and so my involvement is on the infrastructure that processes that data, and because the data being collected in the instrument, they have to find it. They have to find their way back to the academic institutions in the United States and other international partners. And there is not really a direct cable that will actually just, move the data from the South Pole all the way there. Right. So usually the process involves satellites downloading the data in some locations in the United States. And from there is pipelines that will migrate the data to endpoints where they will be further analyzed and so on. But it's the CMB, the South Pole Telescope is one of the one of the greatest success stories. But mind you that it's not the only one. Down in the South Pole right now, there are several experiments that are pushing the frontiers of what they call multi-messenger astrophysics.
Yeah.
And multi-messenger astrophysics is that if you have a problem in astrophysics, you have multiple information conveying the picture about what this phenomenon, what this object that you're studying, it can actually relay information back to you through multiple kinds of science.
Mm-hmm.
So it's not just optical astronomy, it may be infrared, it may be gravitational waves that with LIGO. So the multi-messenger astrophysics efforts out there are really trying to collect as much information from different channels to be able to determine, the big questions in cosmology, right? What is the inflationary period? What is the spectrum of the CMB, background radiation? How does this affect the distribution of galaxies and everything that comes after the era of last ionization back to the present day? All these big questions in cosmology can be addressed, can be tackled by having as much information from different instruments, all looking at different parts of the physical processes that are involved with.
Yeah, and this data is obviously continuously generated, right? So
that is correct. Yes.
Yeah. So could you give me an idea of what is the rate of data we are talking about from these instruments?
I can give you an idea that every time we are actually looking at the data on a daily basis, we're getting a few hundred gigabytes.
Okay.
On every day.
Okay.
And just mind you that down in the South Pole, we are actually having a local little cluster.
Mm-hmm.
I wouldn't call it little, but definitely a piece of infrastructure that already processes the data, somewhat before it even gets sent out. And in fact, there are people from the collaboration from the South Pole Telescope, including my own group,
mm-hmm.
that will be traveling there, typically in the Antarctic winter, Antarctic summer, which is our winter.
Yeah.
That will go there and either do science or even provide maintenance and upgrades to the infrastructure down the South Pole.
Right. Okay. And is there? So, what exactly is the goal of the SPT? What exactly are they? At least currently, what is their primary goal?
Well, the study is to actually look at the CMB power spectrum, and look at the different angular scales of how a structure is being separated, because that spectrum, that CMB spectrum, is the quintessential parameter that will determine how are the galaxies and the later star formation and everything else that follows that are to the present day will actually evolve. So a lot of effort and energy has been spent in really figuring out for the study of the CMB, what is the exact shape of the power spectrum, what is what they call the angular scales, smaller than a few arc minutes and so on.
Mm-hmm.
But the more detail you have on that power spectrum in terms of from the smaller scales to the larger scales, the more confident you are that you built in cosmological evolution models that will correctly predict the observable parameters of the later universe.
Okay, so it's looking at inflation hypothesis. It's looking at the Big Bang itself. So it's really questions around the origin of the universe, right?
It is, yes, indeed.
Okay. I want to jump into another project that you're involved in, Enzo, an adaptive mesh refinement code for astrophysics. So this is adaptive code for fluid flows. So this is computational fluid dynamics meshes you're talking about?
Yes. We just discussed the importance of figuring out the cosmic microwave background spectrum.
Yeah.
All of this information from the experiment are basically generating and determining few key parameters that when you feed them in cosmological models, you can actually design computer simulations that will evolve different scales of the universe from the early universe all the way down to the present universe. Enzo is one of these codes that basically uses, evolves the universe, at least the box of the universe, from the earliest time all the way back to the what we call the time of the last scatter, down to the present time. And that does this combination of cosmological physics and also fluid dynamics, because as matter in the universe is basically effectively can be approximated as a fluid, right? It's a gas, and that when it collapses forms stars. But it's not just gas, though. There is also components that we don't have a fairly good understanding of what is the physics behind this. For example, dark matter. And all of these components of dark matter, fluid that is governing the gas, radiation that is emanating from the stars, shock physics that emanate from colliding sheets of gas together and creating all these different phenomena like turbulence, for example. All of these things can be coded with sets of a number of equations, and you can solve them with various approximations. And when you do this in a three-dimensional space and four-dimensional in terms of integrating forward in time, what emanates from that is the picture of the evolving universe from the earliest time all the way to the present time that will give you rise to the galaxy formation, the star formation. And if you're really going to go down to the nitty-gritty of the present time, you can even though create the host sites of future planetary formation systems.
Yeah.
So Enzo is one of these codes that has the ability to go from these very early times to the later times, and depending on the resolution, you can actually get some very interesting physics started with it. It's not the only code. There are multiple. Back in my day, there were maybe 3 or 4 different codes, but nowadays there is a plethora of different code variants that use different methods, like smooth particle hydrodynamics and other variations. But overall, the objective is: can I study with numerical high precision a problem of the universe and get insight of what's going on?
Right.
I have the equations, but the equations, if I want to basically get an answer, I got to numerically solve them. And when I get the numerical answer back, do I understand what the value is and how does this compare with observations?
Right.
So it's always the game of I can get an answer from any kind of numerical simulation, but does the result compare with what the observational astronomers will tell me about something specific? And through the disagreement is good in a sense that it allows you to go back to your model and refine the parameters in such a way that basically match the data. And of course, it opens up another question: why did you have to make the refinement, the adjustment? How is this justified within our understanding how the physical laws should actually be solved, and and how they govern the state of the universe and its expansion?
Right. Yeah, it brings some memories, Pascal. I was involved in some modeling work in the late 80s with some CFD work, and this was aircraft design. So remember writing some code. The meshing, that CFD mesh, how you do that is is very critical, right? to
right,
how
right,
you
exactly. You mentioned before about this adaptive mesh refinement. Remember, we're talking about a box that captures structure at immense different dynamical scale.
Yeah.
You can have voids empty from complete from matter to sheets that are basically compressed gas in some kind of a sheet kind of a structure, to globules of matter as they try to condense, all the way down to the scale of a star. The dynamical scale in terms of the sizes, going from the large scales down to the small scales, is extremely daunting.
Yeah.
And the only way, you cannot really then spend a lot of computing time trying to put the resolution elements in a part of the simulation box that basically has nothing there, right? So a lot of the effort should be, can I actually do my science where it matters? And that's where adaptive refinement comes into place, where you put you basically resolve with grids the areas of interest what you're studying. And grids and adaptive refinement is one method. The other method is based on what they call smooth particle hydrodynamics. Is if I have an area of the volume where I want to focus, for example, the formation of a galaxy, I will have far more particles resolving that portion of my simulation box and I will have no particles whatsoever in voids, because nothing is happening there in the first place.
Right.
So this adaptivity comes from the very large dynamical scale of the problem.
Mm. Yeah, so you also have another paper that is looking at a specific experiment. So you say that the Lyman alpha forest at redshifts 0.1 to 1.6, good agreement between the large hydrodynamic simulation and the HST Hubble Space Telescope spectra. So this is something very specific that shows.
That's right.
Yeah.
That's, you do the simulations, and then that, if I remember that paper correctly, because it's been a while, it's you create a simulated distribution of the universe, and then you are assuming now you have a star or not a star, a galaxy in this case, that shines light. As this light is going through the intergalactic medium, it gets absorbed by the filamentary structure of the within that intergalactic medium. And from the observer's point of view, you see all these dips in you have this spectrum, this time series of dips in the light as they're coming through the interstellar medium and gets absorbed by different structures. And so you can simulate this. You can pretend you have a point of light, and you shine a straight line through the box, and you can create what we call synthetic spectra. And then you take this spectrum and then you compare to what the observers see.
Right.
And if you have a good agreement, there is definitely a leap of faith here. When you claim you have good agreement, therefore you validate the model. All right. It is a small step forward into making sure that at least we have some command that the input parameter that went into setting it up was not that far away. Now, people can disagree whether it's like, the Hubble constant is like, 72.5 versus 70.6, because it is it's a system with way too many free parameters. And so, varying one parameter to make an agreement may be just achieved by another parameter, varying it somewhere else, right? So, and that's what, from the time to time, from every few years, what we call a new concordance model is built, where it says this is the set of parameters that, to best of our knowledge and best of our calculations, fits largely the picture of the universe as we can measure it with our instrumentation.
Right. Yeah. I mean, the advantage of simulation, obviously, is it gives you flexibility to fine tune the parameters.
Correct.
But the downside, though, might be that you're also tempted to fine tune it so that you can actually match what you observe, but it may not be necessarily true, right?
Well, yes, and also remember that a lot of the times, if you look at how observational astronomy or cosmology in this particular case, you can observe the same, I would say, object. And then a couple of years later, another instrument will go up in space and look at exactly the same object. And then it's not that it's going to validate your observations previously or invalidate them, but it's going to change something, right? And depending on how sensitive your set of equations are, that little something in the properties of that object that you're measuring may be good enough to basically give you a whole different understanding and appreciation of what this object is all about.
Right.
A small parameter change by even a fraction of a percent may change our understanding of what is our perspective of this particular phenomenon or object that the scientific community is studying.
Yeah. You have another paper, Pascal. It's on a completely different topic: tiered financial fraud detection utilizing precision stratified random forest assembly. You want to talk a bit about that?
Yeah, this is something that I am involved with as my capacity as with my Chicago State colleagues, and this was done in terms of like trying to get established computational tools and find a real life example upon which we can apply them. So, for example, a random forest is nothing more than just a bifurcation map of different decision nodes where you can make a decision yes or no.
Yeah.
And you can take these computational tools that is taught to undergraduates or graduate students in computer science and trying to find implementation, landscapes out there. And the major landscape out there is decision-making theory.
Right.
All right. And in decision-making theory, you are trying to make a decision of what is the best course forward, giving multiple choices. And I think that paper is trying to get a real life example, but based on a computational model that is completely agnostic of what this real example is. So my involvement in this paper was on the technical part of decision making for us rather than the specific implementation on the case that you mentioned.
Okay. So in conclusion, Pascal, if, I know that you're involved in a lot of different projects. What is the most exciting thing as you look forward 5 years? What do you think is the most exciting area that you're involved in?
I would say my work within the context of open science grid and in general integrated science infrastructure is the most exciting one. It's not that it's technically very challenging. Of course, there are technical challenges to be overcome, and there's definitely a lot of sweat and tears that have to be shed for making a particular technical implementation stick. But it is the bringing community together to take small steps forward that at some point, the small steps, when you integrate them, become giant leaps.
Right.
And so my involvement in this project as the coordinator for Midscale, or even being involved in other projects as well within the open science community, looking at this multidisciplinary effort in utilizing our understanding of how computing tools work and how they can be best adopted, you see the impact not only on communities that I have been traditionally been affiliated with, right? Let's say physics and astronomy. You see the impact across an entire gamut of science out there. Specifically, let me give you an example, right? Of the times, COVID-19 research, right? The moment that we came to the realization that a lot of computing power has to be spent in coming up with because when you're building a vaccine or you're trying to understand a disease, it's not just simply being in a laboratory mixing chemicals together, right? There is a very significant component in molecular biology, computational biology, that requires computing power. And so when this effort come into place, where it says, well, okay, we have all these institutions out there that they're trying to understand the problem, let's say the COVID-19. Open Science Grid basically said, okay, we're going to open up the doors. We're going to give you as many computer cycles as you need. Fill up, every institution's, queue as much as possible. And then you have this community of that typically was kind of like science and engineering, flooding the gates, trying to get an answer to, a real life problem. A lot of the times, especially in advanced science, people can feel like we kind of isolated from real life problems, but we're not. I mean, we are in all of the things that are happening on the computational side do have real life application. For example, you mentioned CFD right now. Right? The safety, the design of a frame on airplanes really depends of what was your quality of your computer simulations that you designed that wing, right? And where are you going to do this?
Right.
And so nowadays, the computational landscape out there is extremely diverse. You have cloud computing, which is a very important component because it really caters down to the, enables small businesses and startups not to have to spend a lot of money in infrastructure and basically really get their hands dirty, accessing computing power. And you have the big, extremely large machines. Let's say, the one of the fastest computers out there is Summit in Tennessee, and these are lots of GPUs, lots of computing power, and these are for the large, like the kind of things I was talking about earlier with Enzo, the big problems, right? The big problems in science. But the big problems of science may advance our steps forward a little bit, but there is a lot of lateral science that has to also be happening at the same time, and that's where Open Science Grid comes in there. The extent of all the sciences that it covers, it's really makes you feel as part of a larger community. So that's to me is the one of the appeals working there.
Yeah, I mean it's really exciting. It has both the advantage of computing cycles. Any unused computing cycle is a waste, and the marginal cost of using that is zero. So it has to be using that in some fashion is the best outcome.
And it's free,
and it's,
right?
And it's free. So optimizing, the availability of those cycles And then I think the way that it is set up, it appears to me, at least, Pascal, that it kind of encourages collaboration as well, right? Lot of people are coming together. Again, you mentioned COVID as an example. If they can share insights, share experiments, and they're all doing it in a singular platform, I think it's really powerful.
And just remember, one thing I wanted to add is that we're talking about Open Science Grid, but Open Science Grid is the US implementation, right?
Yeah.
There is like networks like this, research network with a common goal in enabling computational workflows exist in all parts of the world, you know,
Yeah.
and not only they exist, let's say the European grid in Europe, they are processes in place, and you know, there's also, you know, work in place already where these two grids can be accessed by both sides of the Atlantic, right? So, and typically we will have, like, you know, our European partners run jobs on the OSG and vice versa.
Yeah.
And so we're talking about an integration that spans the national borders, right, and spans oceans and continents. And, you know, if we can get researchers that basically ignore, you know, the what is a flag and what is a border and focus on the fact that, you know, science is science, regardless of whether it's written in English or Japanese, right? You can actually get a community under the same banner, which is the advancement of science and the betterment of humankind. So to me, it gives you like this beyond the area of cyber infrastructure, becomes an area of, like, you know, human structure. It's like, you know, this a planetary structure in terms of like people pursuing a worthwhile goal as a species rather than as a US or American or a Japanese or a Chinese.
Yeah, and as they say, from the space, you cannot see any national boundaries. So
that's true.
So all we have to do to get to make that happen, Pascal, is to get 8.3 billion people up in space, and they can look down and say, "Wow, you know, there are no countries from there."
That's true. Although, you know, you can always turn on the TV and look at the NASA channel.
Yes.
But there will be those who think that this is actually filmed in some, you know, studio someplace. But we digress.
Right. Yeah. This has been great, Pascal. Thanks so much for spending time with me.
Thank you for the invitation.
Yeah,
I appreciate it.
Good luck with all the research that you're doing.
Thank you so much.
Thank you. Bye.
Hey, bye.